We're going to talk a little bit about multi-threading in C#, and we're going to take a look at how to create threads, how to create tasks, and how to execute parallel processing. So we'll start with a little bit of background on why learning about multi-threading is beneficial. Primarily, if you understand how multi-threading works and the classes that are used in C# to allow multiple threads, then you can design your programs to take advantage of multi-core processors. In C#, you can create threads and you can create tasks. And each of them are used in multi-threading. Tasks allow for asynchronous parallel implementation. Threads execute tasks. So if you create a task and you run it, it is going to run on an open thread. You can create either tasks or threads in C#. If you create a task, it goes into a task pool, and the Windows runtime will determine when to run it using an open thread. This allows the Windows runtime to optimize the use of threads and tasks. If you create a thread, not a task, but a thread, and you start it, it is going to run once you start the thread. Whereas if you create a task, the Windows runtime determines when it should run. So that's one primary difference. Because of the way tasks are handled, they are a little bit more flexible than threads. The Windows runtime optimizes the number of threads required to complete concurrent tasks. It basically takes a look at, what your equipment is, what's currently running, what tasks you need to complete, and then it bases the decision on that. So tasks are pretty flexible. Threads are not flexible. They're explicit. So once you create a thread or, multiple threads and you start them, they will run. Okay? Windows runtime does not optimize them. And so the system is just going to run them when you start them. Because tasks are flexible, they scale better than threads. And what that means is that you can run the program on a larger, more powerful machine, or you can run it on a smaller, less powerful machine. And because the Windows runtime looks at the hardware that you're running, it will always optimize the number of tasks that will run on open threads. And obviously, threads don't do that, right? If you create a thread and you start it, doesn't matter what kind of machine you're on, it's going to run. So we are going to take a little deeper look at tasks, threads, and multi-threading. Because tasks run on a thread, we're going to look at threads first. Okay, and then we are going to take a look at tasks. And while we are looking through all of this, keep in mind that the Universal Windows platform utilizes tasks and not threads. Okay, so console applications you can create threads on. So what are threads? Threads are processes that signify an execution path in a program. So when your program is running different applications, they are basically different execution paths that run on a thread. Each thread defines a unique flow of the program, and the thread use increases the efficiency of an application because the CPU time isn't wasted. And you'll see what that means as we go through examples, but quite often when you are running an application, the CPU has to wait. So maybe you're reading a file or maybe you're accessing a database, but there is wait time involved. And if you use multi-threading, you can take advantage of core processors and multi-core processors, and you can actually run uh, different execution paths at the same time. So we're going to take a look at what a thread is and what a process is, so you kind of fully understand what's going on. So what is a process? Well, in Windows, you can actually see what processes you have running, um, but it is part of the operating system responsible for executing a program or an application. So in your task manager, which you can access just by right-clicking on your taskbar, and that brings you right into the task manager. So I have the newest version of Windows 11, so mine might look a little different than yours. But you can actually see what apps I have running, how much CPU they're using, how much memory, and each app is going to run on a different uh, thread, basically. So a process is used to run an application, and to run the code of the application, the process uses a thread. Okay, so those are the two key points here when we are looking at processes. Okay, they run an application and they use a thread. So a thread is part of the process responsible for executing the application. By default, every application has at least one thread responsible for executing the code, and that thread is called the main thread. So if you don't create any additional threads or tasks in your program, when it executes, it will use the main thread. Okay, so by default, every application is a single threaded application, and it uses the main thread. So you can open any program in Visual Studio, and it doesn't matter how big or small it is. And you can actually see the main thread uh, by adding a little breakpoint. So you can see this is a super short program, and I added a little breakpoint down here where we're pausing the program. Basically, it's waiting for me to press enter or to press a key. So once the program is paused, I can actually pull up the thread panel. It is in the debug menu under Windows and Threads. And so this is what it looks like. Of course, yours might look a little bit different depending on what you're running on your system, what program you're in. But you can see that there is a main thread, and that is basically what the program is using to run. So C# does have a thread class. The thread class can be used to create threads. You can actually set priorities to threads. And if you do that, there are some threads that are going to get a little bit more CPU time or a little less CPU time, depending on the priority that you set. You can provide the current state of the thread, and you can pause threads. And so to do all of these different things with threads, we end up using properties and methods that we will take a look at in a few minutes. Why should we use the thread class? Well, if you have a short program and it doesn't take much computing power to run it, then you probably are not going to use the thread class. The thread class is useful in programs that use a lot of computing power, like graphics, or programs that have a heavy computational load. Okay, maybe programs that access a database where they have to wait to use resources on a server. Okay, those are instances when the thread class can come in handy because it'll speed up your program. By default, your program is going to execute sequentially. If a single method takes time to execute, the other ones are going to have to wait. So I do have a little example. This one is not utilizing threads at all, but these methods that are in main are going to execute sequentially. So if the first method takes quite a while, method 2 and 3 are going to have to wait. And that makes sense if method 2 and 3 are dependent on method 1. However, if they are independent of each other, it really doesn't make sense to make method 2 and method 3 wait for method 1 to finish. Okay, and so that is where multi-threading comes in handy. So let's take a little look at this a little closer. You can see method 1 probably isn't going to take that long to execute. It's got a little for loop, and that's about it. Method 2, you'll notice that we kind of put it to sleep. So we are using a method called sleep, which is part of the thread class. And we haven't created any threads, so it's going to put the main thread to sleep, which in a sense is going to pause the program. Okay, and then when this is paused, method 3 cannot run. So it's just in a kind of a wait state until method 2 wakes up and completes. Okay, so how this looks when it runs, I'm going to throw it in here and run it for you. Okay, so you can see that it's kind of simulating database operations. So this is where it's asleep, and then you can see it completed, and then it finished method 2 and went on to method 3. But there was definitely a pause there, right? And that's because we put it to sleep because we're accessing a database or pretending to access a database. So this kind of situation is why we actually use multi-threading. So to create multiple threads for the different methods to utilize when they're running requires creating a object of the thread class and assigning that to the method using a delegate. And in the thread class, they utilize an action delegate that's built in to the class. And that allows us to pass our methods to the constructor, the new thread constructor, when we are creating a object. So we've got thread, which is our class, T1 is our object. New thread indicates it's going to go to the constructor, and we are passing it a method. The reason we can do that is because, behind the scenes in the class itself, it's utilizing an action delegate. And if you guys remember from delegates, the action delegate can accept parameters, but it doesn't return anything. Okay, so that is how we would create a thread and assign it to a method. And in addition to creating the thread, you can name the thread. Okay, so there is a name property that is part of the thread class that allows us to give a name to the thread, which is just kind of fun, and it helps you identify the different threads. So in our little example, we are going to name the threads. Okay, and so at this point, the thread is created, it has a name, and we need to run it. So to run a thread, you take your thread object and you call the start method. Okay, and you already kind of saw how to put a thread to sleep. All right, so a little bit of a revised example here. We still have method 1, 2, and 3, but now we have created separate threads for each one. And just for fun, we've given each one a name. Down here, we start the 3 threads. Okay, and then we indicate the main thread has ended. So even though we have created 3 separate threads, the main thread is still going to run. Okay, it runs the minute your program starts running. Okay, so that's why we have main thread started, main thread ended. Okay, because at the bottom of your code is when main thread ends. And then if we look, you can see we added some write line statements to the different methods so you could follow what they're doing. So it's just saying the method 1 started. It's going to give you the name of the thread, got the looping going on, and then it tells you when it ends. Now, because this is multiple threads, it's not going to run sequentially like the last one. Okay, and just to point this out, when we run this one, you can see it's in method 1 and it finishes. Then we're in method 2, and here it's pausing. Okay, and then it finishes method 2 and it goes on to method 3. So it's sequential, right? This one is not going to run that way. So you might have, method running, then you'll see messages from method 2, then you'll see messages from method 3, but it's not going to run entirely sequential. Okay, and you can even see looking at the main thread, it ran through all the code in the main thread, but it's still processing the other 3 threads. Okay, so I'm going to go ahead and copy and paste this. Okay, and then we'll go ahead and run it. All right, so we've got method 1. Here we've got method 2. And you can see before method 2 ends, we started the tortoise here, which is we've got method 3. Excuse me. We got method 1, method 3. Delayed starting method 2. So here's method 2. We ended out method 3, and then we finished method 2. And we can run it again, and it'll probably run differently. So again, it's going to run differently depending on, what you have running on your system. So each time you run this, you could get different results. Okay? But the key here is that we are utilizing the main thread plus 3 additional threads to run this program. So how can we see this? Well, let me pause the program and I'll show you a couple different places where you can see not only the name of the thread, okay, but you can see the state of the thread, whether it's running or not. Okay, and one of those places is the locals panel, and then the other one is under debug windows and threads. So let me put the little pause in here. And all I'm going to do is put a breakpoint in. And now I'm going to run it. Okay, and so technically it's still running. So let's lift this up a little bit. And here's my locals section. And so here you can see we've got Speedy Gonzalez. The thread state is stopped because it's not currently running. And then if I go ahead and step over, okay, then we get out of there. So let's run it again. I'll try to get into locals a little bit faster. Oops, not quite fast enough. It's still stopped. Although this last one says it's running. This one is sleeping. So actually you can see a little bit of activity here. The tortoise is asleep, the hare is running, and my first one is stopped. Let's take a look under debug and windows and threads. Now I've got to kind of shrink this section up so you can see that. But here you can see the tortoise and the hare. They are still running. My first one appears to be done. So let me look and see where we're at here. We got Speedy Gonzalez, which was my first one. I've got 1, 2, 3, 4, 5. Yeah, so that one ended, which is why we no longer see it. Okay, but the other two are still running, so you can see them here, and the main thread is still there. Okay, so if you have multiple threads, you can view what the status is of your threads. And 2 different places you can look. I actually like looking in locals because it's a little bit more information than looking in the thread pane. And one other concept here with threads is that the main thread actually creates the child threads, which are the worker threads. So in a multi-threaded program, when you're creating threads, it is the main thread that is creating those. We have looked at a couple of the thread class properties and the methods. This is a more complete list. It's not all of them, but it's the more useful properties and methods. So we've used name. We're also going to be using priority. You will also see current thread being used. Okay, so those 3 we're definitely going to be using. And then as far as methods go, we've used sleep, we've used start, but you can see that there are quite a few different methods that you could actually employ here. For constructors, we already talked about how the action delegate is kind of built into the class. And the procedure that we used to create a thread was the first one, okay, where we use the thread class, give it the object a name equals new thread, and then we pass the name of the method as a parameter. You could also use an anonymous method or a lambda expression. So if I wanted to create that thread, the first thread with an anonymous method, I would use delegate here. Okay, and then I would put all of the code I wanted executed, and then I would start it. And for the Lambda, you can see it is very similar. Obviously, we don't have the anonymous method name. We are using the Lambda operator instead, but the actual code itself is the same. Okay, and then we would start it. As far as the life cycle of a thread goes, the thread is actually going to start when you use the start method, okay, unless it's the main thread. Main thread automatically starts when the program runs. So you can create a thread and not start it, which means it would be in an unstarted state. You can create the thread and start it, but maybe it hasn't started to run, which would put it in a ready state. And then there is a not runnable state. So if you put it to sleep or suspend it for any reason, or maybe it's blocked because something else is running on that particular thread and it has to wait, that would be a non-runnable state. And then the dead state would be it's done executing, or maybe you aborted it. So this next example, I've actually given different priorities to the threads. And the highest priority is going to get more of the CPU time. It should finish first. Below normal is not going to get as much of the processing time. And then above normal should get a little more, but not as much as highest. Okay, so let's run this one and see how these priorities affect the program. And you may notice in the methods, I've got a little bit more going on because I just wanted to utilize some of the properties. So you can see I've got current thread name to access the name associated with the thread that is running. And then I am using current thread is thread pool thread, which basically is asking if the thread is coming from the thread pool. Now, if you use the thread class, it should not be in the thread pool. The threads that come out of the thread pool are from tasks. So if I use the task class here, then it would be coming from the thread pool. But this is not because I'm using the thread class. So I would expect this to be false. Okay, and then we are printing out the priority for the thread. Okay, and then as we're going through the loop, we are printing out the state, the thread state, and then we're printing out a little message that we've ended. So this is going to let you follow exactly what the different threads are doing. Okay, and we're utilizing the properties and the methods. So we'll go up here, main thread started, and you can see we started the hare, we started the tortoise, is the hair part of the thread pool? Now you should see false for all of these. Okay, method one we started using Speedy Gonzalez. Is the tortoise part of the thread pool? Is Speedy part of the thread pool? You'll see it's false for all of them because these are threads. These are not tasks. Then we get into printing out the priority. So the priority for Speedy Gonzalez is the highest. I would expect that one to finish first. Priority for the tortoise is below normal, which is the lowest. And then the hair is above normal. Okay, so we've got method two, method one, and method three. They've all run once. Then we're in the tortoise. That is running. That is method two. Got the hair, method three. Tortoise is running again. We've got the hair running. Got the tortoise running. And that ended. You can see my computer must be busy doing things. Method one ended using Speedy. And then finally method three ended. So let's run this again, because every time we run it, it is going to operate differently. Okay, let's look at this order. So we've got the tortoise ending before the hare. Okay, and this one actually operated a little more like what I would expect because it's got Speedy ending first, and that one had the highest priority. But I can see we're gonna have to do something about tortoise here. All right, why don't we give this one highest also? All right, let's run this one. Interesting. For some reason, it wants to give resources to. Why don't we make this normal and see how it works? And you can see what your different values are, and this is something you can kind of play with. All right, this one is more what I would expect because we would want the tortoise to end last. Okay, but this is something you can play with. Normally, if you wanted something to run before everything else, you would probably only set the priority on that one. Okay, but you can play around with this as much as you want, just to get a feel for how everything works. Okay, so that is threads, and now we're going to move on to tasks. So a task is some work that needs to be completed. Uh, as far as how you create a task, it is very similar to the way you create a thread. The difference is you're going to use the task class instead of the thread class. Also, behind the scenes, tasks are placed into a thread pool where the Windows runtime is going to assign a task to a thread for execution. Threads do not go into the thread pool, and the Windows runtime cannot optimize them. So huge difference kind of under the hood as far as how tasks and threads are handled, but the way you create them is very similar. And because a task runs on a thread, once you create a task, you can actually use the different thread methods in addition to your task methods. Okay. So here is basically the same program that we looked at earlier, but instead of using the thread class, I am now using the task class. Okay, and you can see I'm starting them. Okay, but it is pulling it out of the thread pool. Okay, so this is the exact same program as before, okay, but I am using tasks. Now, one of the properties available for a task is the ID, and that's how you can kind of tell them apart. Tasks do not have a name property the way threads do, so you can't give them a name, but you can access the ID, and that's how you can kind of tell them apart. But here you'll notice that we can still put the thread asleep, just like before, using the thread class. Okay, and this is a sample run. Okay, so you can kind of see what the IDs look like. And as far as the task class goes, it does have its own properties and methods. So I've listed some of them. Okay, and current ID we've already taken a look at. Uh, but it will return the status of the task. And then you can also check to see if it was canceled or if it's been completed. Is faulted means that it threw an exception, an unhandled exception. And then obviously exception is an exception that handled and caused the program to terminate. As far as the methods go, you can kind of see start we've taken a look at. Okay. And then we've got several different wait methods. And so I've got some examples here utilizing the different methods. And one that is kind of nice is, and actually any of the wait methods, because as these programs executed, you probably noticed that the main thread started and ended, and then you could see the other ones still running, which looks kind of weird, but they run independently. So uh, you've got your main thread, and it's going to go through the code, and it's going to start these different tasks, and then it's basically ending uh, because it's run through all the code. But the tasks themselves, which are running on their own threads, are still running. But it does read strange. So what you can do is you can actually use any of the wait methods, and that makes the main thread wait until the task is completed before it finishes. Okay, and here I've got wait any, but t2.wait would also do the exact same thing. The reason I included both and commented one out is so you can kind of see the difference in the syntax. So if you're going to use wait, you actually have to use the task object. Whereas if you're going to use wait all or wait any, then you have to prefix it with task. And then in the parameter, you are sending it, the object you're going to wait on. And with this one, you can see that, it's executing the different tasks, and then the main thread completes after everything is done. Okay, and then without the main wait methods, it actually completes. It looks like it's completing before everything is done. And I think this one may be using wait instead of wait any. But, you can actually copy and paste these and kind of take a look at what they're doing. So this one is also showing status. So let's take a look at this one. All right. So here we have a little different syntax to create our tasks. And we are using the lambda syntax. And because we've got task.run, we don't have to start them. Okay, they're automatically going to be queued to run. Remember, these are tasks, so it's the Windows runtime that determines when to actually uh, give them a thread and get them going, which is why we can check the status. And this is going to pause the completion of the main thread until basically our second task is completed. Okay, and all of them are calling this one little routine where we're passing it our task number. Okay, and that's just a string. Okay, and so that way you can tell which task is running. So here we go. So it starts by running task one, says it's running. Now task two is running. You can see task one was not completed yet. Okay. Task two starts executing. Then we go through the loop. Task two is completed. And then it still says that it's running. We go through the loop. Now task one is completed, and then the main thread is done. And if we run it again, it'll probably run differently, just because, remember, those tasks are placed into the pool. So you can see here, task one was waiting to run, did not have a thread. Task two was actually executing. And then it must have started running task one. And these must be from task one. Then task two started running, and then the main thread ended. As far as the constructors go for the task class, it's the same as the thread, okay? The same exact procedures where you can either, assign the object to a method, you can use an anonymous method, or you can use a lambda expression. And actually in this example, we saw a little different use of a lambda because we actually are telling it to go ahead and start running. So instead of task one equals new task, we've got task one equals task dot run. So we got threads. We have tasks. We have a thread class, we have a task class, and we also have a parallel class. So the parallel class allows for parallel processing, which makes sense if you have methods that you want to run that are not dependent on each other. Windows Runtime is going to kind of take a look at your code. It's going to figure out, the level of parallelism that your program needs to run efficiently. Okay, and so the parallel class includes three different methods: parallel invoke, parallel for, and parallel for each. So invoke actually is going to run your tasks. Parallel for is an alternative to using a for loop. And parallel for each is an alternative to using a for each loop. Okay, so the program that I have for an example is using parallel for. Okay, so let's take a look. So here we have 5 different tasks, and parallel invoke is going to start them. Okay, and so for each one, we've got a lambda expression set up. Now we have no parameters, and we're basically calling a run task method. And we're going to pass a number and another random number. Okay, so the first number is the task, and the second number is basically the limit for our for loop. So we're going to run through a little for loop, and whatever that number is how many times it's going to run through. So let's take a look down here at run task. So first we're going to indicate what task we are running and what the limit is. Okay. And then we have our for loop. And basically we are just adding the numbers together, calculating a sum, and then we're going to print that out. Okay, so this is a traditional for loop. Okay, and then we have the parallel for loop. So the results of the two are going to be the same. But when you do a parallel for, it is going to go through the iterations all at the same time. Okay? The end result is going to be the same, okay? But how it processes is going to be a little bit different. Okay? And so you can kind of see in the output here, it starts, this particular run started with task 5, limit of 19, results with the for loop. Here we go. And then results with the parallel for loop. You can see that it does not finish processing the parallel for, but it goes ahead and starts on our next task. Okay, and it gives the results of the for loop there, or it starts processing it, and then it's starting task 2. So at this point, we have 3 different tasks running in parallel. We have task 5, task 4, task 2. Results for task 2's for loop. And you can see task 2 sum. And then here's the results for a parallel for loop. And this was task 4. So we had task 5, task 4, task 2. Okay. Task 5 is still doing the parallel for loop. Task 4 was doing the parallel for loop. And you can see here now it's done. Task 2, we have a regular for loop. And here it is starting the parallel one. Okay. And then task 1 starts. So you can see all of these are running at the same time. So for task 1, we've got the for loop here. Okay, and in the results, I am printing the task number so it can help you kind of follow what it's doing. And then we've got our parallel for loop. This would be for task 1. So it's starting that. Task 3 then begins. And you can see we have the for loop. And then it starts working on our parallel for loop. And the parallel for loop has taken the longest. So you can see finally we are getting the results from that. Okay, and then you can kind of see the order that the different tasks are finishing. So what we've been looking at so far, we are assuming that everything is going to run perfectly and that we don't need to cancel anything, and it's not going to throw an exception. So honestly, that's not very real world. In the real world, you may want to cancel. And in the real world, at any given time, you can get an exception. So um, we have created an example with exception handling. And so we're kind of taking a look at this little example. And so I've got something that I'm calling a fun method. And I'm passing it a string and then a reference to first time, which is a Boolean. Okay, so let's look down here at fun method. We're bringing in the string, which is basically our run number. And then we're bringing in the Boolean. So we indicate which run number we are processing. We have a very large number for a count. And we create something called a cancellation token. So if you want to be able to cancel a task or a thread, you need one of these. You create an object or an instance of the cancellation token source class. And the reason I'm passing first time is that I've decided to cancel that one. So the first task that comes through here is canceled and the rest are not. So I take my instance and I call cancel, and then I set first time to false. And so only one of those method calls is going to be canceled. Okay. Then in my try block, I call long running task. I pass it the count, and I also pass it the cancellation token source dot token. So basically I'm passing it the cancellation token, this little instance here, so that I could cancel if I wanted to. And then you can see for exception handling, I am catching task canceled exception. Okay, and this is a custom exception that I've created down here. Okay, so that's not part of the C language. It's created down here in the throw. Okay, so that's kind of what's going on. Let's take a look at long running task. So we're bringing in this cancellation token, which is going to allow us to see if a cancellation was requested, and if it was, it allows us to throw the exception. So the process here is that you request a cancellation. That does not necessarily mean it's going to be canceled immediately. Okay? You actually have to check to see if it was requested, and then you can throw your exception. To see how long this long-running task actually runs, I have used the stopwatch class, which is actually part of C#. You can create a new stopwatch object, and then you can measure the milliseconds. So I've created this little stopwatch object, and I start it running. And then we get into the long-running task commands. So here we have our loop. And if you remember, count is a pretty large number. Okay? So that's how many times it's going to go through the loop. And then to make this extra long, I have a very large delay. Okay? On the very first iteration, I indicate that it's processing. Obviously, I didn't want to do it on every iteration because we would just have screenfuls of this message. So I only do it the first time. And then I'm checking to see if the task is meant to be canceled. And if it is, we throw the exception. Okay, right after the loop ends, we call the stop method for our stopwatch. I create a little time object. Get a little format here for the elapsed time. And then I print it out. So you can see how much time this takes. So the output for this, it starts processing the first run. A long running task has started. That's coming from here. Then as it gets into the for loop, it says long running task is processing. The first one is the one that I have canceled. Okay. So you can see here, if first time, that is the one that we have canceled. So you can then see a task has been canceled and an exception has been thrown, which indicates it's been handled. Okay, so here is the message that gets thrown. it is going to get thrown up here to the catch, which is handling it. And we still have fun method, the second and the third kind of round to complete. Okay, so the first run is canceled, but then you can see that it starts the second one. Okay, so it started when it says it's processing, it's in the loop. And then when the loop is finished, we are printing out how long it took. And then we do the same thing for the third one. So the correct way to cancel is to do it this way, where you use the object that you created with cancellation token source. Okay, you use that object to call cancel. Understand that it's not going to cancel right away. Okay, it's basically kind of flagged it for a cancellation. So you do need to check to see if the cancellation was requested, and then you need to throw the exception. Okay, that is the correct way to process a cancellation. And if you do it, trying to use any other techniques, you tend to get an exception error. Okay, so that is kind of the summary of tasks, threads, and parallel processing. Please realize that these procedures are not appropriate in every environment. In fact, if you add threads to programs that don't need them, you may actually increase the processing time. So keep that in mind. They are appropriate for applications that have heavy computing requirements. And graphics is one of the best examples of that. But also any program that is using lots of computations that are complicated. Okay. Those types of applications are going to be using a lot of resources, in which case, tasks, threads, and parallel processing makes sense.